Okay, our attendance is not good, so we'll wait for a while. Okay, maybe 2 to 3 minutes. Okay, attendance is still low, but we should begin. Okay, just because we only have 2 classes left, and the final week will be, for the exam, right? So we will have 2 more classes. So this class will finish this set of slides about streaming sketching, and we will have another written assignments. Okay, that's the last assignment, right? And today we will also release the final project starting from 6 p.m. The hard hand will join and present the project details. And feel free to ask questions. So this is about image segmentation using the annotations that all the students have prepared. And we selected some high quality results. Okay, those that are not so good, we actually remove them. And we have a code that trained using UNet, which is a segmentation model, which works well. But we will provide a list of other models and for you to play with and test out. Okay, and there are existing implementations. You can also implement it yourself if you have bandwidth. And so the final project due is, I think, by Wednesday. Okay, by Wednesday of the last week, because we need to finalize that. We need to mark many projects. Okay, so if you need more time, you need to let us know. Okay, we don't want everyone to submit very late. Okay, it's not that difficult if you look at it's in the final weeks. Okay, next week you feel free to do that. Okay, so the 2 weeks later, Wednesday. Okay, so basically 2 weeks. Right? So and 1 week for the written assignments and 2 weeks for the final project. Okay, if you need a 1 or 2 days of extension, if you have justified reasons, we'll consider that. Okay, but we need some time to mark it. Okay, we need to finalize the grade the Monday after last week. Okay, so we cannot grade so many projects in just a couple of days. And so, yeah, today, 6 p.m., Bahatan will go through the project instructions to you guys. And the data has been collected and put into a folder. Okay, and the loading part has been written for you. Okay, you don't have to write the loading part, how to load each image and its polygons, right? So, and even we provided a sample of how you can visualize the masks and how to translate the polygons to masks, right? Because you have polygons and everything inside the polygon is a pixel that is in the cell, right? So, and outside the polygon, right, it's not a pixel in the cell, right? Then we have a pixel mask. Each pixel is either 0 or 1. 1 means it's a pixel for the cell, for a particular, for a cell. Otherwise, it's a background. Okay. All these have been done for you. All you need to do is understand the code and try some other models. Even a sample model has been done for you. Okay. And we also provide that you can refer to, right? So different kind of models. We'll provide potentially 8 models for you to select. And if you have interest, you can also select some other more advanced models. There must be some new models, more latest models. These 8 models are kind of probably 2 years ago what we have, right? So if you have interest, you can use some new segmentation models in deep learning. Right? Okay, so
Professor,
yes.
I missed the assignment part, so we're gonna have another written assignment.
Yeah, we have another assignment. This lecture. Basically, we will have like a counting, counting sketch where we have instructions for you to study, and then use what we learned here, do some randomized algorithm analysis. Okay, and actually, this is a very famous sketch. So if you read through some instructions, you should be able to work it out yourself, right? But basically, as long as you are familiar with Markov inequality, chain of bound, all those stuff. Okay, so you should be able to understand it, okay? Because this is a well-founded sketch, okay, for counting all elements. So basically, for each element, you want to estimate the count, and you will use this count. And today we will give more examples of how to derive these kind of sketches and the quality bounds, which is on the other bound. And we'll finish this this slide, and then Bahatan will go through the final project, and we will then after this slide we will look at a few like how to collect data, right, from the open data repository, and how to crawl tweets, all those things, right? So previously they are some of them are like mini projects. Now we will provide the code to you guys. If you have time, you can try it out. If you don't have time and later you might need it, you can get the code, and later when you need it, let's say to do some Twitter crawling, you can get the code and play with it, right? So they will not be required a submission. Let me see, there's a chat. Oh yeah, so the final project can be, I think it's written in the syllabus. You can either do individual work. I understand it's a pandemic, the remote teaching. A lot of students cannot find teammates, right? So, but if you are able to form teams, right? So you know some friends that are, you can work with. You are welcome to form teams of no more than 4 students. Right? Each team should have no more than 4 students, right? At most 4 students. And if you are a team, then you should prepare for a more advanced, projects, right? So I mean, it's the same project, and if you want to choose your own projects, let's say, right? So you need to let me know, okay? But we strongly encourage you to choose our projects. I would suggest projects, because some projects that you are doing on your own, there's a concern from the department that some projects are used for other courses like deep learning or some other data science courses we have, like data mining. So that's why we prepare a particular data set and then let everyone work on that data set for this particular course. So it's difficult to use. And if you can justify that your project is equally difficult and it's not used elsewhere, then we may consider that. But I think we have done very rich preparation for you guys to study and like load the data set. You can skip a lot of efforts already, right? and you are already working on the sweet spot. Okay, so the dirty work has been done, like how to clean the file and put into the main memory objects. That's already done for you. So this project potentially is the easiest way is to follow this project and work on some tasks. Okay, so we will have 8 models for you to choose. For example, there's a Deep Lab. Right? So Deep Lab has 3 versions at least. Right? So Deep Lab 1, 2, 3, and maybe 3 plus. Okay, 4 versions. If you have a team that is working on segmentation, maybe you want to try all these Deep Lab models and compare the pros and cons. Right? So, and so basically, I think at least as a team project, you should try more than one model, okay? And make it like clearly present why you choose these models, and you do some comparison, which model performs better, which is not so good, right? So because if you look at segmentation, it's basically image, pixel-wise classification, right? Whether a pixel is foreground or background, binary classification, but for each pixel, right? So you will be able to report some metrics. Okay, so I hope I answered the question. Oh yeah, so for PhD students, actually, there should be a presentation, right? So, but because this time we only have 1 PhD student, that's a little bit special. So you can present at the final exam time, okay? And or if you want, we can schedule another meeting when you are ready, and just present to me. And we will share the video with every student. That's also fine. Kamal, is it okay? Yeah, because previously we will have maybe 4 to 5 PhD student teams, right? So, but this time, because of pandemic, we only have 1 PhD student, right? So, in that case, we can make it more flexible. We don't need a class to do it. Okay. Yeah, just schedule a meeting with me, right? So we see whether on the last week both of us will work out, and then you can do a quick presentation. Maybe TAs will also be there, give some ratings. Okay, thank you. All right, so what we have seen earlier is a streaming model, right? So we will have numbers coming, right? And it's coming forever, so you cannot keep all the data, right? And there's so many data, you can also just say you want a quick update and a quick query of the results, okay? And because this restriction will always have some error, except for the random sampling example we see earlier, right? So if you do the random sampling, you can always do exact sample kind of thing, okay? But for other tasks, you have to introduce some small error by randomization. And we have seen this earlier, right? So, for example, when we can do the counting distinct elements, and get some intuition that we will use a random hashing to make sure if you see a stream of elements, right? And each distinct element in your current stream is forming a set of elements, okay? And each element is uniformly mapped into a range, right? This is by, universal hashing that we talked about earlier, right? And after that, basically, if it's uniformly distributed, you can compute the, n, the number of distinct element as, as a set S, right? So how many different elements are there? As the m, the domain size divided by m, the minimum element. Okay, so this is how we estimate that. And the last time we spent some time, earlier we spent some time describe how a universal function can be constructed, right? So basically we can use ax plus b in the ZP domain, p is a prime, okay? And so this is just a 2-wise independent, right? So if we want a k-wise independent, right? So which means, so these events, xi1 equal to ai1, x2 equal to a2, xk equal to a2, right? So k of them, the joint probability is equal to the product of their individual probability, which means these k events are totally independent, right? This is this is stricter, right? So then we should have a more higher mode polynomial function, right? So again, these numbers are also in ZP, right? F is in ZP. But this is cubic. And the reason we do this is think about it, right? So if we have we have 4 unknowns, right? F0, F1, F2, F3, right? And then we have x values, right? So because this is 4-wise independent, So if we give these x basically is this value, right? And the y is this value on the right hand side. And we give these 4 numbers here, right? This will be 4 linear equations, okay? We have 4 linear equations, we have 4 unknowns, right? So we will give a unique solution, okay? So this is allow us to do the unique mapping, totally uniform mapping. The proof is, I think here we have a proof, but the concrete proof is similar to here. I hope you still have the, still remember that. Okay, so then using this universal hashing, we say that such a hash function can really be achieved, right? Then what we can do is we can do FM sketch. And here we are saying, hey, we want to estimate the number of different elements you see so far in the string, right? The cardinality of set S, okay? It can be estimated as the domain size divided by the minimum element you see. Of course, the minimum element to hashed value, the minimum hashed value of an element you see so far, okay? And we show that this value is actually very close to D, right? So if you bound it between D by 6 and the 6D, right? So we show that this is within it with a constant probability, okay? This is within it, within this bound with a constant probability. And so here, let me see, we should put it here, okay? So here you can replace 6 with any value, right? So you can get very close to 1, okay? Then this left-hand side becomes D, right-hand side becomes D, right? And then it's basically saying they are equal. Okay? So now the discrete elements is almost equal to M divided by, right? At least with very high probability, okay? If you have a very high probability, you repeat many, many times, then the failure probability is very, very low, decrease exponentially, right? So as long as we can prove that we just need a constant number of ones, right? And then we can show that by logarithm number of trials, we will have some guarantee that we are within this range, okay? And so in our proof, we use 6, right? But this can be replaced as C. Of course, this probably will become another value, but it's a function of C, right? Because C is a constant, this is still constant. It's just the impact how many trials you need to take, okay? So here we show a proof that on the left-hand side and right-hand side, probably less than 1 by 6. So in the middle, the probability in this range, the probability is larger than or equal to 2/3. Okay? And we use some tricks that you still remember. It's quite complicated, but keep in mind, so these numbers can be replaced, right? So for example, this 6 you can replace with C, and then when you do this range, okay, it's really becomes C. So you can replace it with a constant. You can derive similar conclusions. It's just that because it's uniform, right? 6 by D become maybe C by D, right? So then you can derive something similar. Okay? So the conclusion actually holds if you want to reduce 6 to close to 1. Okay, you want to make it a very tight one, right? But here we just use a particular number for ease of clarification. Right? So for FM sketch, actually you can get very, very close, D very close to M divided by mean, right? Can be very, very close to D as long as you try enough time, right? And here, each trial is independent because each time you try a different hash function, right? So its hash function is sampled from the universal hashing family, right? So if each time independently you get a probability of this, right? Different times you fail is just 1 by 3, right? 1 by 3 times 1 by 3 is 1 by 9. And then if the third time you fail is 1 by 27, right? And if you try this, you can see that as you try 10 times, it's almost impossible that you will fail. Okay, so that's FM sketch. And then we show the majority algorithm. And the last time what we show is that, so firstly, what is the majority definition? Right? So what's the problem first, okay? So the problem is actually saying that, majority means you are not just the let's say if you have 3 apples, 2 oranges, and maybe 2 bananas, right? What's a majority? There's no majority, even if you have the most number of apples, 3, right? But the majority means you should have more than 50%, right? 3 apples, but you have 7 elements. It's less than 50%. So there's no majority. We really need a majority, okay? So is there any element that's truly the majority, more than 50%? If that's the case, what's that element? Okay, if you have 4 apples, then 2 orange and 2 banana, then it becomes a majority. But if it's 3, then it's not a majority. Okay. And the last time we showed that if you want to answer this question exactly, especially the difficulty part is the first question, right? Well, it's exactly more than 50% of times that appears, right? So if you want to answer this exactly, you will see a space low bound of linear. Okay, and we show by proof by contradiction that it's impossible that you will not having, by construction basically. Right? So you cannot get a less than linear in order to exactly answer this question. Okay, and then we explained that we can have a simplified version of this problem definition. Right? So it's a weaker problem. Okay, so it says that if there exists some element that occurs more than 50%, your algorithm must operate that element. Right? But if it's not, right, there's no majority, then your algorithm can operate anything. So there's no, it's undefined basically. Right? But whether you have majority or not, there's no requirement. So if in case you really have the majority, okay, then you should operate that majority when your algorithm ends, your streaming algorithm. Okay. So how can we do that? Anyone has an idea? Yeah, just to brainstorm a little bit. Right, so who want to have a try? This is actually a very simple problem. Okay. All right, so I don't see any volunteers. Let's see the algorithm. So firstly, you will store in A1, right? So, and a counter 1. So A1 is the first element you see. Remember, our data stream is A1, A2, A3, right? So the elements you see. Okay. And then whenever you see a new element, right? So what do you want to do? Right? So yeah, this is actually not difficult. You can easily work it out, right? So whenever you see a new element, AI is the ith element, right? You check whether it's the same as the current element you store, right? You only store one element, okay? If the same element, apple and apple come again, what you do is you add the counter value. Okay? You have a counter initially 1, okay? Else, right? Else, if the counter is larger than 0, right? So what you do is, else means, the element is different from the item. Right? Then you reduce the counter value. Okay, and but this is only happens if your counter is larger than 0. Right? Otherwise, you will store AI in the static counter to store the new AI. So let's take a look at an example of what this means. So let's construct an example that have a majority, because this is a weaker problem. Right? If there exists majority, then this should really happen. Okay, and then we show why this is required. Let's try. Let's say we have A, B, C, A, B, C, A. Let me see whether it's a majority. Okay, let's try this. Okay, so here we have A, B, C, A, B, C, A. I hope you can see it. So the first A1, right, because we store A1 and the counter. Right? So what we do is very simple. We say, hey, now the current element is A, and my counter is 1 apple. Okay, and then B. Okay, B is you see B, right? Because my stored element is A, but now A2 is B. Okay, so it's different. So we should go to the else branch. Okay, and by this time we say, hey, the counter is 1, which means hey, apple is A is occupying, right? We are right now counting A, but we see a B. So what we do is we counter, we cancel A, right? Because it's a different function. We cancel A. This go to 0. Okay, and next we will look at C. Okay, then when we look at C, right? So this is A3. Okay, the stored item, no, the stored item A, it's not equal to C, right? Then we look at the counter. Counter larger than 0, no, the counter is 0. Okay, so which means, hey, even though we have an A, but it's like the initial case, we don't have anything, right? Because it's already canceled, right? And then we will store C and a 1. Okay, so let me erase this. A becomes C, and this number becomes C. Okay, now we have C1. Okay, just store the C and the 1. Okay. And now let's look at A. Right? So if we look at A, we will cancel this again. because it is okay? Because it's not equal to stored item, right? But the counter original 1, then cancel, okay? And C 0, okay? Now, now we look at B, okay? This B item. Right? And when we see B, it's again not equal, right? We go to this else branch. And now because it is 0, like it's already canceled out, there's nothing exists anymore, right? So we will replace B and 1, B1, okay? And then we see C again, right? And B and C are not equal. We will cancel this, right? We will cancel this, but the element is B, right? The counter is 0, okay? And then we see A again, and because this counter is 0, then it's like a non-exist. We can just put A here, A1. And then we see A again, then we have A2, right? So by the end, we will see, hey, the stored item is A, and A is really the majority, right? We have 4 A's, 50% already, because BC, BC are also 4 numbers, right? So we have the majority at the end. Who can tell me why this is correct, right? So here we are just going through a great, a particular example, right? Looking nice, right? So, but how do you know that for any data stream, this will return majority if there's a majority? Who can tell me? Right, so the answer is this, right? So you always have some item there, right? And you can, if the item is a majority, which means, so this item either cancels some other element, right? If let's say the majority is A, okay, but this A is not equal to your current stored item. That item must appear in the stream, okay? So then you will cancel it, right? You can cancel a other item, let's say B, okay? Or your another A can cause the, if you happen to be A in the stored item, you can cause the A to be plus, okay? So counter can be plus. So let's see why this is correct, right? Because you have at most, you have at least a half of them are A, right? Okay, and you don't have so many other things, right? So the other things at most cancel with those A's. After canceling all the A's, you still have an A left. Okay. Oh, because we require larger than, it's not larger than equal to. 4 is not enough. You need a 5. Okay. If it's strictly larger than half, right? So you know that you have so many A's. Right? In the worst case, it's not equal to some data in the stream, then you will cancel them, cancel all. But you cancel these B, C, D, you cancel, but you have so many already. You have half of them to cancel, but this, you have more than half. There's another A that will cause you to be stored there or not canceled out by other elements, right? I hope this is intuitive. Any questions regarding this algorithm? So just keep in mind, right? So initially you have an element, you will always keep it a counter. But when you see something different from your current element, you will cancel the counter, okay? But if the counter is larger than 0, you will cancel. If the counter is not, it's 0 already, that's like the item is not there, okay? Right, you can just store the new element with counter 1, okay? But if you see the same element, you will add its counter. Then it can be canceled by some other different items. Okay, so let's move on. So next is a frequent algorithm. So the majority requires you to have more than 50%, right? So if you are the most frequent item, right, but you are not the majority. Let's say 3 apple to peach to banana, for example, right? So that in that case, apple is a mode, okay, MODE mode. Right? It's the most frequent item, but it's not the majority. Now we want to find the frequent items, okay? A list of frequent items, okay? So again, as we said, our algorithm should have a hopefully constant space, right? A small number of space, and most logarithm space, okay? So here you can see we just store an element and it's a counter, okay? It's really, you can think about it as logarithm bits, right? Because the integer is logarithm to m, okay? You don't want to store entire string that you see, okay? And the update should be quick, right? So this algorithm is constant time. just add some counters depending on the condition. So similarly, for frequent algorithm, we also want this to happen, right? So how can we do that? So here, the idea is similar. If you look at the previous algorithm, what we do is we store one element. Store one element. Okay. So here we can do is we can store k items being counted. So then we can have more items than just the most frequent one, right? So majority. Right? But the list will initially, of course, be empty because you see nothing. Right? So the algorithm works as follows. If AI is on the list, which means, because you keep a list of k items, right? If you go beyond the k items, you need to kick out some existing items, okay? So the procedure to do that is as follows, right? So if AI is on the list, then its associated counter is just incremented by 1, okay? Otherwise, if the list is less than k items, right? So you only see apple, orange, banana, right? So, but you can keep 5 fruits in your list, right? Each with a counter. Then of course you just append another one like pineapple to the end with counter, okay? Because you have the space for that. Right? Now the space is k, or you can say k log n, if you think about the counter, the 32 bits of log n, that's log of 4G, 4 bits. Otherwise, if your list only has, let's say, apple, peach, and banana, it's 4, right? Then you see an orange, okay? And your k is 3, only 3 fruits. Then what you can do is you use orange to cancel every element's counter, okay? Apple, peach, and the bananas counter, all in different value, okay? So, and if you see any elements of counter this time becomes 0, it's canceled out to 0, basically, right? If that's the case, you remove the element, right? So the reason we want to do that is because we wanna because we only allow k items. Right? Something becomes counter 0, it means that element is no longer there on the list, right? So that you can remove it, then you will have this more nicer condition hold, okay? All right, so let's see why this is correct. Okay, firstly, let's do some analysis, okay? So here's the conclusion. We will give the details of conclusion in the next few slides, okay? So what guarantee do we have here, okay? So we should have some guarantee, right? So the guarantee that we have here is that the counter, it's always an underestimate of the actual count, okay? So you will not, so if you have, let's say, 3,000 bananas, right? So the estimated counter on your list will always be less than 3,000, okay? But hopefully not too much smaller than that. Right? The epsilon is decided by this name, right? Maybe this is 3,000, but you are different by 100, okay? Right. So if we think about 100, that means actually your n and k, right? K is like n is 100 times k, right? So maybe you have so many items that your list can be a lot smaller, only 1% of all the items you need to know. Okay, so that looks a little bit nicer, but really this is for frequent items. Okay? Really the count is very frequent, but the k list. So the longer the k list, of course, the smaller the error. Right? But it's really how if your item, right? So this is counting frequent items, right? If your item account for 1% or 10% of it's running to n. Okay? If this k is not running to n, then it's not very effective. Let's say your count is altogether 10, right? And this thing itself can go to 100. Then it's not interesting. Right? The count should be actually the count itself should be a fraction n, say alpha. Okay? And this is again some fraction n. But this k can be adjusted much smaller than alpha, the portion that you care about. So this is maybe 20% of n, which is a very frequent item, okay? Or maybe even 1%, right? You can adjust k to be 1,000 or 10,000, which is still very affordable because, modern memory, 1 GB is nothing, okay? We can have this 1 billion, right? And you can really get a lot of frequent items. Right? So maybe 1 billion is crazy, right? 1 million, for example, right? Like a few megabytes or tens of megabytes of memory, then you will be able to count many frequent items, right? let's say you want to count everything that is larger than 1%. Okay, the frequency is larger than 1% of the whole stream. And okay. Now you can set this as a 1 million, right? Then 1 million, you know, it's a 10 to the power of -6. Right? Okay, so this is much more smaller than this. This is 10 to the power of -2. Okay. So compare with this amount, this error is really small. So this is really for frequent items, okay, not for infrequent items. So what do we mean by infrequent items? Infrequent items are that you have this nice guarantee, right? If your element is not on the list, right, your count is going to lessen this value. So it's infrequent. This is like really some frequency bound that you want your count to be a few times larger. Okay, then your error becomes small. Okay, so this is saying, for example, let's go back to that we allow 1 million items in our memory buffer. Okay, in this key items in the list. Then what we can do is, of course, you can use dictionary. That's in Python. It's the same thing. Okay. Then, so you know, this is n by 1 million. So 1 million. Okay. So n can be much larger, of course. So like 1 billion or something. But divided by 1 million becomes 1,000. But the count is can be maybe 1% of billions, be much larger. Okay. And if you are less than this, right? You are less than 1 million, 1 by 1 million percentage of the whole stream size, then you are not on the list. Okay? So anything that is on the list must have guarantee that you are at least this. Okay? If you are not on the list, it's guaranteed that you are not beyond this amount. If you are beyond this amount, you must be on this K item list. So this is pretty nice, right? And your error is an underestimate, but not too much by this epsilon, right? Any questions? Okay, so if there's no questions, let's take a look at how this algorithm runs. Right, so let's give an example of let me see, how to give a good example. A, B, B, C, C, D, D, C, maybe D, E, F, A, B, okay, let's just do some random streams. Okay, let's consider this stream in the order from left to right. Okay, I hope this is okay. And we have A, B, C, D, E basically. Right, F. Okay, we have A, B, C, D, E, F, and we just want a buffer of size 3. Okay, three different numbers. Okay, so K is equal to 3. So what we will do is, let's assume that firstly we are at this A. Okay, let me change the code. Let's assume we are now at this A. Right, so what we have is we have a list that keeps, you can think about the Python dictionary, A1, okay? And then we will move to this A, okay? This A. Then according to this algorithm, we'll update A2, right? And then we'll go to this B. And then because, you know, it's less than K, okay, we will have B1. And we will go to this B, and we'll go to B2, right? So what's interesting is when we look, so CC will also get to C1, C2. Okay? Now we reach the K items, right? We go to else branch. So what's interesting here is that next, let's look at D. Right? D is not equal to any elements here. Okay, it's basically, it's else. It's not on the list. Okay, and because it's not ABC, D is, you know, canceled. Right? So here we will decrement every counter by 1. So this 2 becomes 1. This 2 becomes 1, this 2 becomes 1. Okay? Basically, you know, a different item that is not on the list will cancel every counter. Okay, this is what maybe here this example is trying to tell you. Okay? And then we will look at A again, and we will increment to 2. Okay? And we'll look at D again, we'll increment this back to 2. And we'll look at E. And when you have E, you know, this becomes 1, this becomes 1 because it's not on the list, ABC. And this will become 0, right? Okay. When this becomes 0, we'll delete the item. Okay, keep in mind, because if you have a count equal to 0, it's like you are non-existent. So this go back to 2 items. Then we'll look at F. Then F will come here and 1. Okay. And then we'll look at C again, and it cancels. Basically, this step should cancel every element because these become 0. It's like they are all numbers. Okay. And then you will count D. All right, so the becomes D. Yeah, so D. So this is how the algorithm looks like. So yeah, so basically this is the explaining this process here. Okay. It's not pretty obvious that we have this guarantee. So this guarantee looks nice, but it's not obvious how we can have this guarantee. Okay, and so let me see. Yeah, so yeah, there's a question. Is K always a predefined value? Yeah, K is a budget. Okay, K is a budget of your memory size that you can afford to use. Just one more. Let me send a link to the hard hand so that you can join. All right, so let's continue. All right, let's continue. All right, so here, let's prove that we do have this, because from previous example, it looks like it cancels everything. Right? So, but because these elements are not that frequent, okay, compared with the whole string, ABC only appears 3 times. It's not that frequent, okay? And if you have something really frequent appear a lot of times compared to the entire string, then you will stay on the list, okay? So D, Kamo, can you clarify your question? D is frequent?
Do you mean that D is the frequent one? Because D is on the list only. Well, what is the answer of this one? I mean, frequent algorithm will output what
No,
is string?
D is on the list.
Character?
That doesn't mean it must be frequent, right? If it's not on the list, it's not frequent. Okay.
Okay. Okay.
D is on the list doesn't mean that it must be frequent. If it's not on the list, it must be infrequent. It's okay. But some infrequent elements can slip into the list because they cancel something and happen a new element or something, just like the previous example. It's okay.
Okay.
Yeah, okay. But if you're on the list, your estimate will be bounded by this number, okay? Right, so basically if you're on the list, most of the time you tend to be frequent, right? You are not canceled a lot. Right? After canceling, you still have some elements, right? But there's no guarantee it must be frequent, okay? But if you are not on the list, it must be infrequent. Okay, let's look at the proof of this. So the key is you think about, in the previous algorithm, when AI is limited, what does that mean? Right? So that means, for example, you have an AI, okay, on the list, and you have a counter K. So, so here we are saying this. So you think about it, right? So we are still considering a stream of like this, right? So let's assume that you have a particular AI here, okay? This AI is not getting on the list, right? It's unlucky because, there's no space on the list for you, and you are not one of the elements. If you are one of the elements on the list, one of the key elements, your counter will be added. Right? So you are not on the list, but there's nothing. Right? So what you will do is you will cancel some elements on the list, each they are counted by 1. So basically you cancel K of them. Right? These K items are there because they appeared previously in the stream K times, okay? In K places. You basically cancel because if their counter is incremented each time they appear. Right? So basically cancel out K items previously in the list. Right? So I hope this is intuitive to you guys. Let's see where it is. Here. Okay. So if AI is eliminated, right, because it's not on the K element list and there are already K items there, then K different symbols on the list are also eliminated before you are also eliminated. Oh yeah, so one student asked, which ones are frequent in my previous example, right? Because we use k equal to 3, right? And if you look at our example, it's like around 10 or 11 elements. 11 by 3 is a small number, right? 3 point something, okay? But you need to be much larger than this number. Your frequency should be much larger than this number to be considered frequent, okay? Right? And you will stay on the list. Basically, in our previous example, the elements are still relatively evenly distributed. So nothing is particularly frequent because we only have a very small list to illustrate the process. Okay. Yeah, we don't have particularly frequent ones. Of course, those ABC I think are relatively frequent ones, but they are not enough to stay on the list because we have this requirement. Okay. Right. So, because they are less than this, basically, if you look at the previous calculation. I forgot the example earlier. I randomly created them. Okay. But if you are frequent enough, right? So you will stay on the list. But some infrequent items may also flip there, like D. Okay, let's continue. Yeah. Yeah. So I don't remember, but this n is maybe 11, but k plus 1 is 4, right? K is 3. So this is maybe less than 3, like 2 point something. Okay, right? 2 point something. Okay, something or 3. Anyway, you can see the proof and go back to our previous example. It should be clear. I don't remember the concrete numbers in the previous one. It should be in the video. So here you can think about, right? If AI is eliminated, that means, you know, k items in previous in the list that get into your list, right? Each element has a counter k minus 1. Minus 1 means minus 1 occurrence. Okay, are eliminated. Right. So this is what we have to convince you here. So that means each elimination, right? So in this algorithm, we don't have much elimination. Some are added counter, right? Some are added to the list with counter 1. Only one case we will decrement counter. That the list is full, but you cannot find your element in the list. Right? So each such elimination, the third case, will eliminate k plus 1 different symbols, right? So besides your AI, which you cannot insert in the list right now, you will eliminate k items previously in the list. Right? So that's from here to here. Okay. So therefore, you think about at most, right? So you know each time you see an element, if it's belongs to case 3, where you will eliminate list, right? So if you think about this case 1, this case 2, these are case 3. Right? If you see an element and it belongs to case 3, it will eliminate, cancel k plus 1 elements, right? Itself and the k other elements. Right? And we know that the entire list only have n items. Okay? So that means you can only eliminate so many n items. Right? So you will eliminate how many times? Right? How many times you will enter case 3? Right? It's so many times. Right? Is this clear? I hope this is okay for you. So now let's look at this. Right. So we are saying that if you are on the list, add a counter, it's fine. Right? If you are not the list has less than k, that's also fine. Right? But the worst case is the case 3. When you see your element, it's not on the list, list 4, then you will decrement every counter. Okay. And this thing itself will be called so many times. Okay. But each time you think about a particular element, right? Particular, let's say a particular element A, right? It will suffer from that element only by minus its counter by 1. Okay, and you at most this thing can happen so many times, right? To cancel A, so you at most minus. So your actual counter of A at most is canceled by so many times. It's okay. So that's why the end estimation is bounded by this. Any question about this proof? Okay, I don't see any questions. Yeah, let's move on. So this basically proves this, and you know, so the other, if S is not on the list, right? So then your count must be less than this, right? Less than or equal to this, because if your count is larger than this, you will never be canceled, right? Right? Because you, at most, you know, you will be canceled by elements different from you for so many times. Okay, if your counter is, let's say you will be canceled for 10 times, but you have counter 11, right? At least you have one count left. So you will stay on the list. So in our previous example, if you are not staying on the list, that basically means you are not frequent enough. Okay, if your frequency is larger than this, maybe previous example equal to this, you can go back to check. If it's larger than this, then you will surely stay on the K list. Right? Okay, any questions about the analysis? Is this guaranteed? These two guarantees? Okay, so the nice thing about this is, for example, you can allocate 1 million, 1 million items, right, in your dictionary. This does not consume a lot of memory. So item may be character size, and the counter may be an integer, right? So you have maybe 1 million integers. It's not a big number in your memory, okay? But you can count, a large string, right? So you can, that's ever counting forever, okay? And you just need to keep these K items to be frequent. Right? So this is quite useful, for example, if you are detecting, let's say one example is you are doing security monitoring, right? And for different IP addresses, right? So each AI is an IP address. You see their frequency, right? And then you keep a list of them, right? And you just keep away maybe a 1 million or maybe even less, right? 10,000, right? And if you see a lot of them with a very large count, they are probably doing, denial of service attack, or this kind of, they are attacking you, repeatedly sending stuff to you, right? And then you can blacklist them, right? So this is one potential application, right? And you don't want a lot of memory, or you keep every visit in the log, right? Even if you can keep everything in the log, but you don't keep them in memory, you keep them in a log file. Right? And the way you do analysis, you still just want to stream this file once using some streaming algorithm, right? Okay, so this is a frequent item. So next is our last application, right? To familiarize you with how we design this kind of sketch. Right? And this is probably the most difficult example. Right? So let's go through it. So this is called the second moment. So what is a moment? Here we have a few definitions. Okay, so f as a number of occurrence of symbol s in the string. Okay, so remember we have different symbols. We can consider them in the domain of 1, 2 to n. Okay. So what is, let's say we call this item j. What is fj? Fj is how many times this element j, ai equal to j basically. How many j's you see in the string, right? This is frequency. F is frequency of symbol s. Okay. So we have the concept called a piece frequency moment of the string. Okay, it's defined something like this. This is pretty much close to LP norm if you know what is LP norm, but LP norm has take a p, right? So cancels this power. Okay, if you don't cancel this power, then it's called a moment. Okay, but here each element is the frequency of each symbol. So here let's take a look at some special case, and then we will give an example. The first case is that p equal to 0. P equal to 0 is called the number of distinct symbols. And we will see why this is the case using an example. If p equal to 1 is exactly n, how many elements you have in the string. Okay? And p equal to 2, it will be what we want to do. Right? So the second moment. Okay? Second moment. Right? P equal to 2. Okay? And p equal to infinity is actually the most frequent element. Right? So this is like the mode. So the mode. Right? So now let's take a look at a particular example, right? So instead of using 1 to n to represent the symbols, maybe we can use ABC. Okay. Let's consider a string something like A, B, C, A, B, A, A, B. So maybe C. Okay. Let's consider this string. Okay. I hope this will help you clarify the concept. All right, so now let's assume that our domain, right? So our domain is more than these three numbers. Okay, our domain, you can take a value A, B, C, and D. Right? This will help us enhance some distinct symbols because some symbols may not appear. So we have entire domain, 1, 2, 3, 4, but it's A, B, C, D, and D never appears. So now let's think about what is FA. Who can tell me what is FA? Number of occurrences with the symbol A in the stream. What is FA? Who can tell me what is FA in the stream? Yeah, 3. Okay, I see Jing giving A, that's 3. Okay. What is FB? What is FB in the stream? Who can tell me? Yeah, it's 3. Okay. And what is FC in the stream? C is 4. Okay. Oh, C is also 3. Right? So let's add a difference. Okay, let's add another C. Okay. Otherwise, there's not much difference. C. Okay, let's assume there are 4. C equal to 4. Right? Now, what is D? FD, frequency of D. Who can tell me? 0. Good. Okay. So let's assume that we have these data items coming, but 3, 3, 4, 0 as a frequency. So then what we can do is, so what is the zeroth frequency moment? Who can tell me? How do we compute it? So this is, if A is 0, right, so the P is 0, okay, plus if B is 0, plus if C is 0, okay, plus if D is 0, okay, 0, 0. So sorry, I think this is not clear. Let's use 2 lines. There's no point to say one. Right, so that's why. So anything to the power of 0 is 1. 1. That's why we want to define this. So if you have some element never appear to the power of 0, we want to define that. So in that case, you have only 3 items. Right? This is 3. These are distinct symbols. You only have A, B, C. You don't have D. Right? So that's even if you have an E, but that's the same. So if E is also there, right? So your answer is still 3. It's a number discrete with 0 frequency. Is it okay? I hope it is okay. Right, so now we look at if P equal to 1. P equal to 1 is pretty simple, right? This is 1, this is 1, this is 1. It's just adding these numbers, right? 3, 3, 4. Okay, it's 10, right? So there are 10 elements here. This is very simple, right? So you have 3 A's occurred here, 3 B's occurred here, 4 C's occurred here. And the total size, of course, is the length of this. Okay, it's N. So that's not so interesting, basically. So this is what we are really working on. So who can tell me what's the answer of this? Second frequency moment for this stream? Any idea? So it is 4. Okay, let's see what it's. Right. So basically we know that we should have quadratic. Right. So this thing is 0 anyway. Okay, and this is 9 plus 9, right? Plus 16. Okay. So this is 25 plus 9, 34. Yeah, answer is correct. Right. So this is second frequency moment. So, but what's the use of 34? Right? So it seems that it's not so useful. We'll, in the next slide, we'll say that second moment is useful. Okay, but this is useful because it's like we are counting distinct elements, like in our FM sketch. Right? We counted the FM sketch. Right? And this, if you use string, you just keep a counter. Any item counts, you just add 1. Okay, so you can add a sketch, but that sketch is pretty simple. It's just a counter of elements. The second moment, here we are talking about second. The zeroth moment is FM sketch. Okay. One's moment is not interesting, but one's moment for different items, A, B, C, that estimation is count mean sketch that you will see in your assignment. Okay. And if you sum all those elements, that's not so interesting. It's just the length of speed. Okay. So the second moment is interesting. Okay. 34. It's not easy to compute. We will see how to compute that, and then we will see how to compute that more space and time efficiently, right? So by maintaining a sketch, okay? And so remember that in naively computing, you need to maintain the entire stream, right? Because this A may appear long after this A. Right? So in order to get this, you need to go through the entire stream. Okay? It's not easy. Right? You still need a streaming algorithm to more efficiently compute this. Okay? Otherwise, of course you can maintain a counter like here for each element. But then you have m elements, this becomes linear to the number of different elements. What if you don't have, let's say if this m is a domain of IP address, right? So you need to maintain all the IP addresses, which is 2 to the power 32. Okay? Then the space is huge, right? So we want a sketch algorithm for that. And then in the extreme case is P infinity. Right? So P infinity may not look so interesting because anything to the power infinity is infinity, right? Okay? But here we have a 1 by P. So this is called L infinity norm. Okay? So this is, if you cancel it back, this becomes the frequency of the most frequent elements. Okay? This is because if you divide, so how to say this? So if you divide this sum by the most frequent element, let's say this is the element A, okay, to the power P, right? And then you times AP, right? Let's first move this out. Okay. So these two actually can cancel, but we don't cancel them. Right? We kind of construct them. So this thing is A, if divided by A to the power P. Right? Well, A is the most frequent. The other items, this thing actually goes to 0. Right? So because it's smaller than, okay? Goes to, less than 1. It's a number of Q to the power P, where Q is less than 1. And if you P go to infinity, this thing will go to 0. Okay? And only this term back. And this term is to the power P and cancels with P. That's why you get A. A is the frequency of the most frequent element. So you can count also most frequent element if you maintain, this again is not a moment already. Right? So this you need to divide by P. Then you are counting the most frequent element. Is this okay? Right. So if you have a question, feel free to ask. Now let's look at why this is interesting. My second moment doesn't seem to make much sense initially. Right? So for this frequent previous stream 34, what's the use of it? Right? So this is actually useful because we want to compute the variance of element frequency in the stream. For example, we want some fairness, right? So we don't want some element to appear too frequently while others are not appearing a lot. Right? So then how is the frequency? Right? So if you remember, we have FA, FB, FC, FD, right? Then we have this is 3, 3, 4, 0. Right? So what's the variance of it? This variance may be okay, but if you have another distribution which is 1,000, so this is 1 million, and this may be 10. Then this variance is huge, right? So it's not so good in terms of fairness, right? And maybe this is a target that is frequently visited. Right? So if you want to estimate the variance of the element frequency, right, then second moment will be useful. Okay. Let's take a look at why this is the case. Just one more. Let me see. But Halahan, are you here?
Yes, I'm here.
Oh, okay. So in that case, I think you can present the final project first, and then I will take a break, and then I will continue with the second moment. Okay?
Okay, sure.
Yeah. Let me this and allow you to share the screen.
Can you please make me co-host? I cannot share screen.
Yeah, I'm trying to, just one more. Okay, you are the co-host now. Okay.
Hello all, can you hear me?
Yeah, I can hear you.
I think, yeah. So everybody here be fine. If there is an issue, just let me know. So I'm sharing my screen and let's start. Okay, so you remember you did a great job in annotating all those Petri dish images. So now we want to do some segmentation on those images. We want to move this research work forward. So here our job would be, at first, we have to select a state-of-the-art semantic segmentation model from a provided list. And we will use it in IPSC image dataset that you annotated. And we will check how we can customize and fine tune our model so that it's trained for this IPSC images. And after the training, we have to find out what was the performance and accuracy of our model. So at the end of the day, we have to compare which model performed best. And then we have to present your segmentation results along with your model accuracy and everything. And then you have to, that's important, so you have to describe them in a self-explanatory report. So this is our goal. We will learn about segmentation, loss parameters, and then we will definitely work on in a challenging and important research problem, and we can treat those models as a black box. We will prepare the input so that input and we'll get the output, but we would learn how to use them. And we don't have to understand the model completely, but we have to read the API and code lightly, and need to read the paper lightly. So here, this is the goal would be, you have done a great job in annotating those images. That has already been done. And we provide you some codes so that based on those image annotations, we will get images with masks. So it would be something like that. We will have the image and we will have their binary mask. So whenever there is a colony image in place, it would be white point there, white pixel. All the other places, it would be black pixel, something like that. And then this has already been done, and you will get the code of this section. So you have already done this one, and the code would be provided. And then we have a limited number of images, so we have to increase the image size by data augmentation. And then you have to select a segmentation model, and then we will train the segmentation model. So this one we have to do. And after that, so when the segmentation model is trained, it would be something like that. We provide the input image, and it will give us the output, output image with annotation. So then we will measure what's the pixel accuracy, what is the mean intersection over union, and you have to report all of them in your final report, and also include the 10 best segmentation results in the report. So in the requirement, model list, we have provided it from slide 7 to 17. Actually, it's from 8 to 18. So sorry, I have to update this. I will update this. So UNet. So we will give you already an implementation for your reference. Then we will, the implementation is on UNet. So as you will have already an example of running semantic segmentation model, you are not allowed to use UNet, but you are free to use any other semantic segmentation models provided in the list. Groups have multiple members, have to select at least 2 models, more is encouraged, and compare the results. Use it in also we have already. So semantic segmentation is recognizing and understanding an image in a pixel level. So in our case, we are interested in colony pixel. So we have to do, we have to find out all those pixels where a colony is, and we have to identify it. And by doing that, we would not differentiate between one colony and another colony. So all colonies will treat just as same. If there is a colony pixel, just make it white, something like that, and do this annotation. And here, like in all those semantic segmentation models, like this is the basic structure. Definitely, like it's basic, and then there would be lots of stuff on top of it to fine tune it. So there would be a sequence of like convolutional encoder, and then there would be a decoder. And encoder, like at the end of the encoding, it just gives us like what is there in that image. And in this decoding path, we get like whatever it is, where it is in that image. So, and there is some skip sequence. So you can definitely read about it later. So this is the core thing of any segmentation, symmetric segmentation model. So here now the segmentation list that you can pick any of them. So this is weekly or semi-supervised learning DCNN, then FCN. So just like FCN fully connected layer neural network. So forward path and backward path, and then there's segmentation results. Oh, okay. By the way, so for all those models, we have provided the paper and also the GitHub link that you can use. So we'd like to add that, like, though we have provided this one, if you find any better implementation of those models, feel free to use that GitHub implementation. So you are not bound to use only this implementation, any of this implementation. So then fully connected Deus nets and another. So it's kind of like dilated convolution. So if you try this, you will get some bonus points. Look, I could not find lots of tutorial or reference for this. So we are going to like give you some bonus for trying this model. And we would like to see like how it works. And DeepLab and DeepLab version 2. So it's again convolutional, and then fully connected conditional random fields in here, and then it gives you the output. So there are lots of references for those, and I have added the GitHub link. Sorry, I think it crashed somehow. My apologies. Okay, and then DeepLab version 3 and version 3 plus. So like after this like encoder module, so they have added a decoder modules in version 3. DeepLab version 3, and then UNet++. You are not allowed to use UNet, but you can explore this UNet++ model. Fast FCN, definitely. Let's try. You can try this too. Gated SCNN. You can explore it, and I found like it's good for video segmentation. But you can try to see whether how good it works in our images. HRNet, same thing. Like it was good for video. Let's see if it works for our images. And then if you think like there are some better like segmentation model, and it gives better performance, because all the models we have included up to from 2015 to 2020. And maybe in 2021, there is a better implementation, or in 2020 or 2019, there was a very good implementation like model that we have missed to include. So you are welcome to try that, but I think it would be better if you get permission from Dr. Ian before working on that. So yes, so use it on our IPSC dataset. So the dataset is provided in here. So and dataset also the code where like you can prepare the mask, and there is also the unit implementation, implementation there. So you can see how unit is working, and then you can just replace it with your segmentation model. And introduce how to your customer fine-tuning model. You remember, like we have a limited set of images, so we would like to increase the number of images. So it's not like we'll copy the same thing again and again. So we have to do some augmentation to those images. So you can flip and rotate the image to get a new image. So it would be something like this. So from one image, you may get like 4 images. It's up to you to explore. And you remember, like as we have to, as you are doing the operation on image, we have to do the same operation for the mask. So yeah, as the image, when you transform the image, the location of the colony would change. So the location of the colony in the mask, we also need to have those in the same location as the image. So augmentation part, like the code we will provide augmentation part is not implemented there. So you have to implement it yourself, but it's not a lots of coding, and you can refer to this one, this GitHub link to see how augmentation is done. And metrics, yes. So after you do this, like you select your model, you divide your code into training set and testing set, and do the training. After the training, we want to measure like how good, what's the performance of our selected selected model. So that's why like okay. Here, like we can do like pixel accuracy, like % of pixel classified correctly. So what percentage of like cell colonies were like classified correctly, and IOU intersection over union. So you can read about this in here, or so this is our image with ground truth. So this should be the result. And say in our prediction, like our segmentation, symmetric segmentation gives us this result. So we have to find out the intersection. Intersection is just this intersection, this. So this one, and our union is this one. So it would be area of this region divided by area of like this region. So it would always definitely, like it would be anything from 0 to 1, but not more than that. So yeah, so area of overlap, area of union. So this is another metric that we have to use to measure like what's the performance of our model. And then, so the base segmentation results. So include those in your report. So it would be something like that. There would be maybe 3 columns. In one first column, it would be the input image, and the second one, like your annotated image. So, and then third one is like what's the prediction of your trained model is. So here, as I told you, like we have already done testing on UNet. So in UNet, for this image, for this Petri dish, that ground truth, like annotated location was here, and then you see the prediction is here. So you see, like, UNet is doing a decent job in like segmenting the image. So let's see how our other models are doing. So yeah, so you can, as like you can do in your computer if it has GPU, but from our experience it may take lots of time. So we recommend you to use Google Colab. So you can you can see you can check this out as a reference, and also like how to you can add all those images, like upload all those images in Google Drive, and here is a link how to connect those Google Drive images to Google Colab. So you can explore those resources. And here, if I click on this, there are lots of semantic segmentation with implementation in here. So you feel free to explore this, and if you think like those can perform better than the list we have provided, yes, definitely, like just talk to Dr. Ian, and if he approves, please go for that. So that was my presentation. So I'll just hand over like the presentation to Dr. Ian. Thank you.
Okay, thank you, Pahan. Yeah. So
okay, so I will not leave, because if you have any questions, so how to stop sharing? Yeah. Yes, okay. Please.
Yeah, any questions from the audience, from the students? So basically, it's a project, because of the time constraint, we already prepared the data loading part, and it's loaded into a memory, main memory object. Okay, and then you can use that object and put into your model's input, and then train different kind of models. And Pahan has already provided some list of models that you can try out. And if you are a individual, like doing it individually, right? So you just need to choose one model. If you are working as a group, at least choosing two models and compare the results. Okay, and UNet is already provided. So basically you have a whole functioning program that you can study, and then you will replace the UNet with other models and see whether these models performs well, and sometimes even better. Okay. Yeah, so we will have three things released. Okay, so today, one is this video for today's class. Second is this final project, dataset and the Jupyter notebook file with UNet, and you replace the UNet, or you can continue working on this file with another model. Okay, so and finally we will have a homework for the current streaming algorithm, slide. Okay, we will have the second written assignment. And any other questions? So the slide prepared by Pahan will be shared, and along with Jupyter Notebook and with the data set. So the data set is a folder, and we already write the code for you guys. Directly call our function, you will be able to load all the data set into main memory as the images and also their annotations. Right? The annotations need to be converted into binary bitmaps, right? So 2D bitmaps, and that's also done for you. Okay, so you can read the code and you will understand what things are happening. Okay, and then basically everything up to where you need to put those things into the model are already done. You don't need to pass the annotations yourself. Okay, if you have no questions, let's take a 10-minute break, and after that we will take attendance and we will continue to finish, the second moment. Thank you. Thank you, Pahan, for the presentation.
Thank you, Dr. Ian. Thank you all.
Mm-hmm. Thanks. Yeah, have a good evening then. Okay, so any questions regarding the project? If you have no question, we will come back maybe 6:35. Okay, so then in that case, we will come back 6:35. So the project will be pretty cool. I mean, you previously have manually annotated, right? So now you can see, hey, after you train a model, and the model will predict those things for you. Right? You don't have to manually, you know how painful it is to do that one by one on your own. Right? So probably just to do 1 or 2 images. And be sure, I think Hadan did mention, be sure you cut the data set into training data set, test data set. Right? So you don't want to do the prediction on the training data set. Okay, but I think we already did that for you. You can just, basically, we have an example for you using UNet. Just to follow that example and replace that model with some other models. If you want to implement your own model, that's even better, right? So, but so that's purely implementing Keras, by the way. So TensorFlow 2.0 is Keras. Okay, but you can also use existing libraries, right? So, but do make sure you understand a little bit how the model works, especially the input and some of the design key ideas and the output, right? So because you need to write a report in addition to the code. You write a report along with the project. Right? So you will submit a Jupyter Notebook file with your code, right? Along with a report of what you did, describe what you did, and what's the result you achieved. Okay. If you have multiple models, how different models compare with each other, which model you think is the best. Okay, thank you, and I will see you in 10 minutes. Okay, so let's begin. We'll first take a quick attendance. We'll sample some students. Let me see. Okay, yeah. So one thing is that so even though maybe many of you haven't taken the deep learning course, that's fine. Okay, so the purpose of the final project allow you to, once you have the data and just some sample code, you will be able to embed and use some other models, like data science models, to replacing this model and see how it works. Okay. It's allowed that you directly call the library of others or using part of the code of others on GitHub. Okay. As long as you can make the segmentation work with other models that we designate, that would be good enough. All right, so let's take attendance. I think the other list, Kamal is here. As I see you are here, so I will just take you. Okay. That's sample. Sai Sanjay.
Sir, hi sir, I'm Brian sir. My mic is not working, sir, so I'm talking in my phone.
I understand.
I'm sorry. Thank you, sir.
Okay. Sai Rasi.
Present, Professor.
Let me see. So can maybe I didn't.
I'm present, Professor Sai Rashi.
Okay, thank you.
Thank you.
Gayatri. Are you?
Yes, Professor.
Okay, thank you. Chun Yao Chen, are you here? Chun Yao Chen, no. I will call 3 times. Okay. Tom.
Hello. Excuse me, I'm here.
Oh, okay. I think Tom. Are you here, Tom?
Yeah, I'm here.
Okay. Alakhaya. All right. So, are you here?
Present, sir.
Sun Kang.
Yes, I'm here.
Okay. Peida Lee. No.
I'm sorry, I'm here.
Oh, okay.
Professor, I'm here, Pidali.
All right, so I will call 3 times. Okay. Aditya.
I'm here, Professor.
Okay, thank you. Harish.
Yes, sir, I'm here.
Okay. Pravasini.
I'm here.
Thank you. Taylor.
Oh, I'm here.
Okay. Sravan. Kalyan. No. Katha.
Yes, Professor, I'm.
Okay. Thank you. Piyush.
Professor, I'm here.
Okay. Trenton.
I'm also here. I'm with Piyush.
Oh, you're Piyush, right? So yeah, but I'm calling Trenton.
Yeah. Hold up.
Trenton, are you here?
We're both here.
Oh, okay, got it.
Thank you.
You're welcome. Kalyani.
Oh, present, sir.
Okay. Ziming Wen, are you here? Ziming Wen, no. Crashy.
Here, Professor.
Okay, thank you. So that's all for the attendance. Let's continue.
Sir, this is Shravan. I'm here.
Who is talking? Sorry.
Shravan. Sorry, Shravan.
Well, let me see. So did I cross you? Oh, you're here, right?
Yeah.
Okay. So, okay. All right, let's continue. Let find the slide.
Professor Kamal is here.
Yeah, I called you. I actually texted you because I see you were here. I saw earlier. So and you are only.
Oh, sorry for that. I was.
No worries. Yeah.
Okay, thank you very much.
Welcome. All right, so let's continue. All right, so the reason we want to compute the second moment is actually we can use it to directly compute the variance of the element frequency. Okay, let's see why this is the case. Right. So firstly, what is the variance of the element frequency? There's a student, Pranavi. I think a zooming one is not. Right, so other student I'll take. Right, so no worries. Where's my mouse? All right, so let's continue. Okay. Yeah. So
no switches.
Huh?
No switches. No switches.
No switch.
Excuse me?
There's no gas too.
Right, so I just unmuted. Oh, okay. If you have anything you want to communicate, just unmute yourself. Right, so let's continue. Yeah, so let's see what's the variance? What's the variance of the frequency for the element frequency for different elements in your string? Okay, so you can compute it like this. So you have altogether m elements, right? And each element, you have the total string length is n, right? So you have m elements. This is on average how many times an element appears, right? So this is the expectation. Okay, this is the actual frequency of a particular item, S single S. Okay, so this is the fs minus the average. Okay, that's the expectation. Then you take a square and then you take an average. That's square of the bias. Right? That's exactly the definition of the variance of the element frequency. Okay, I hope you can see that. So we want to say that if we can estimate the second moment, we can directly compute from second moment to compute the variance of the element frequency, which we will be interested. So in order to see how you can compute this, right? You can expand it, right? This is a minus b squared, right? Equal to a squared minus 2ab plus b squared. Okay. And next we can, so you can take the summation each of the three terms, right? The first term is something here. Okay. Now what if you take the summation over into the second term? And so basically we are saying that you glue this together with this, right? So the interesting thing you need to see is that summation over fs is n, okay, if you still remember. But because this is summation of all the frequencies, right? A appears 3 times, B appears 3 times, C appears 4 times, then it's 10, okay? So this summation over fs is n. So if you look at this, then the second term is basically, this thing plus this in n, right? This is n squared, the other m here, this is m squared, okay? So this is a minus 2. This is basically, the second term is minus 2, m squared, n squared, okay? The third term is plus, right? Plus this thing, but you see this thing is a run to s, right? So you sum m times, it's like a times m, but you divide by n. So these two cancels basically. So you plus 1 n squared, m squared back, okay? So this is what's happening for the third term, okay? So minus twice something and plus 1 thing back is just one something, one term, okay? So this is how you go from here to here. So now let's take a look at it. Right? So firstly, you should notice this is our second moment. Right? So this is exactly the second moment we care about. Right? And assume that we have a way that whenever we see items coming, we can always maintain the second moment with reasonable accuracy. Right? We can, let's say we can estimate the second moment 34. Right? We can estimate with reasonable accuracy. Maybe we'll estimate to be 35 or 32. Right? So, but it's fine. Right? So it's really close. Right? Then we can give a reasonable estimate also to the variance. Okay. So you may say, hey, why once we know this second moment, we know the entire variance, right? Because m is the number of distinct elements. You should know this. Right? N is how many elements you see. Right? You should keep track of this just with a counter. Okay. And this is again the n. Okay. So once you know this, you can easily compute it. The others are the constants that you should know, right? Then you can compute this variance. So the problem of computing the variance of element frequency can be boiled down to just estimate this second moment, right? Any questions? All right, so if this is okay, then let's just consider how to compute this second minimum. So basically, every element, you have a frequency, square them, and then take the sum, how we can estimate it. And with reasonable accuracy, and with a limited space. So we actually also maintain a count like metric. So here's how we do that. It's again approximate, but we want the error to be small. So here we are doing something like for each symbol, right, that you can take, orange, a banana, apple, for each element, each fruit, for example, you map to a number, which either positive one or negative one. But you want to map them with equal probability, right? So let's say apple is to 1 with 50%, okay? So in order to do that, you need to define a hash function. Right? So let's assume that whenever you throw a fruit here, let's say apple, right? The hash function will tell you whether you should map to positive one or negative one, right? So it's return. This is basically a hash function that maps each element, right, each symbol into either positive or negative. But we want to make sure when we randomly sample a function h from the hash family, it will map your, let's say a particular item 2, let's say it's an apple, right, to 1 with 50% probably, to -1 with 50%, right, depending on which hash function you sample. You may, maybe in the hash family, 50% of the hash function maps apple to 1, another 50% of the hash function maps to -1. Okay. So here we actually require so-called a four-wise independent function. We'll see why. Okay, so we'll use this four-wise independence conclusion in later slides when we prove the error bound. Okay. But how can we compute a four-wise independent function, right? So previously we know that if we can have this function to be four-wise independent, right? A polynomial of mode 3. But the problem is that it's not mapped to this domain. Right? This domain is only 2 values, 1 or -1. But previously, we are mapping to ZP. Right? So for example, if your prime is 7, then you are mapping to 0, 1, all the way to 6. Right? But here we only allow 2 values, map to 0, -1 and 1. It's not the original one. Right? So how can we know this thing itself is four-wise independent. Right? Can we construct another hash function that can map to a new domain like this, but still satisfy four-wise independence? So here the function is, we take the leading 4 bits, right? So leading bit of the 4 bits, right? So if you compute this hash function, you can write it as a binary number, a number as in binary form, right? 1001, right? So the first bit, the leading bit, is what you take care of. The others you don't need to worry about, okay? Right. And then the leading bit, if it's 1, then you map to 1. If the leading bit is 0, you map to 0, -1, okay? So that's a new function we construct. Basically, we use the original four-wise independent function on ZP, but we post-process this ZP to see which, the first bit, if it's 1, then we map to 1. If it's 0, the bit is 0, we map to -1. Okay, this is how we construct another function. And we want to show that this new hash function is still four-wise independent, right? So how can we show that? So firstly, if you look at, this is probability, right? So here we are saying that, remember this is a function like this, right? So x is s, right? So like an apple, right? So if you put an apple and it gives you 1, maybe you put an orange, this gives you -1, etc. Right? So for a particular setting of alpha, beta, gamma, delta, right? So it's a 1, 1 - 1 combination, right? What's the probability that the joint probability? Right? What's each item's probability, right? So each item's probability is 1 by 2. Okay, I hope you can see that. This is because if you look at the, let's say your S element put here, right? So depending on, because your sample a hash function from a hash family where F1, F0 to F3 are randomly sampled from ZP, right? And when you randomly sample them from ZP, we know that if it's a prime, it will map into a uniform distribution, right? So basically you will see, if you look at your number, right? So those starting from 1 and those from 0s, there are equal number of them, right? Because since the other bits are the same, but this is the first bit, they're equal number of them, okay? And they are uniformly distributed, okay? So then because they are equal numbers, then whether you for in this group or for in this group, right? So the probability equal, it's 1 by 2, right? And this holds for the other element t that we put here, right? T and this beta, right? 1 or minus 1, okay? So this is also 1 by 2. And because we have 4 terms, altogether it becomes 1 by 2 to the power 4, okay? So this assumes that, you know, this is each property 1 by 2, right? If we take the product term, then it's 1 by 2 to the power 4. What we want to show is that they are equal, right? Because if, you know, this joint event is equal to each event taking product, then it means that each event itself is independent, right? And this is 4-wise independence we showed earlier, okay? So can we show that this probability, right? This probability is also equal to this, right? The answer is yes. So the reason is very simple, right? So if you look at the, you know, XS, right? So let's take a look. Again, it's by the number, right? So you think about, so how many, let's say X equal to, let's say a particular bit is the leading bit 1. How many elements has that leading bit equal to 1? There are 2 to the power of k minus 1, right? So basically, you think about a number of k bits, right? So we have k bits, right? But we want to fix the first bit to a particular value, right? So not, the rest of them you can change arbitrarily. There are 2 to the power of k minus 1, so many. Okay? So if you look at how many elements satisfy this requirement, this is 2 to the power of k minus 1, right? And here, similarly, we also have 2 to the power of k minus 1 elements satisfy this requirement, and this requirement, right? And so if you look at the combination of them, right? So you take the product of them, right? So, you know, which means your S for in that particular half of this entire group, right? This particular half. And your B for in a particular half, depending on beta is 1 or minus 1, right? Maybe for in this one, U is for in this group, and the S is for in this group, right? This probability is actually to the power 4, okay, will be equal to this number, right? Now, what's the total possible numbers, right? So, you know, if you don't restrict these cases, the bases are very large, right? So it's basically entire k-bits can change. Right? It's a 2k, 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 2k to the power 4. Right? Then again, it's 2 to the power 4. Right? If you compute that, the possible combinations of all values, right? So basically, we are saying that these values can become 1, 1, minus 1, minus 1, or 1, minus 1, minus 1, 1, or something. Right? So for a particular setting of alpha, beta, gamma, delta, right? So you can show that it falls in, basically it restricts the first bit, right? And it leaves the rest k minus 1 bit flexible. But this is also the case. Right? So if you think about these are different cases, take a product. There are so many cases when you consider them together. Okay, so these are so many cases for a particular combination of alpha, beta, gamma. Yeah. Well, if you don't have this restriction, all possible, the base is this. If you divide these two numbers, again, it's a 1 by system. Okay, so this basically proves that this is these two are equal. Okay, the first is pretty simple, right? This is 1 by 2. Okay, so this is not so simple. You need to see, hey, X. So there are so many cases. So there are 2 to the power k minus 1 cases here, and there are also 2 to the power k minus 1 cases here. Okay, numbers are like that, and similar, and there's a combination of these 4 numbers. There are so many combinations. Well, all the possible combinations of these. But then among these combinations of the bits will satisfy this condition. Okay, so this is also 1 by system. So this basically proves, you know, the left-hand side are equal, and this is a 4-wise independent for the new domain here. Okay, this is for the new domain. Any questions so far? I hope it is fine. Okay, now that we have a powerful tool, which is a 4-wise independent function, right? Then what we can do is we can, again, you need to sample each time, right? Otherwise, you don't have the sample hash function randomly. Basically, we hash each fi from ZP. Okay. So if we do something like this, then we can, what our second moment algorithm maintains is not maintaining the entire stream, but maintain a summation, right? So this is, again, just like the previous examples. We maintain a counter, a summation, right? It's very nice, okay? It's very space efficient. It's maybe just a number, right? So, but whenever you see a new element, right, so what you do is, so keep in mind, so what is XS? That you have S, then you do a hashing of it. The XS is either -1 or 1, okay? So whenever you see an element S, AI is equal to S, then you hash it, you get XS, and then add this hashed 1 or -1 to the sum. Each time S exists in true. So this is pretty functionable, right? So you can easily implement such an algorithm. Right? It's very simple. Whenever new S comes in, you hash it and add to the current sum. So you can see that the final sum will be equal to this. If this is not obvious, then just think about, let's say A, AA, B, B, CA, okay, something like this, and maybe CAA. Right? Let's assume that you know, A is hashed to 1, B and C are hashed to -1. Okay, so whenever you see here, you will hash to 1, 1, right? So the current summation, you will, the first time it's 1, the second time 2, right? -1 becomes 1 again, -1 again becomes 0, -1 becomes -1, right? Summation. Okay, and then if you see here, this is 1 again, but -1 plus 1 is 1, and then this 2. Right? So basically, you know, the summation, this summation you maintain is initially 1, and then you see another 1 becomes 2. And -1 becomes 1 again, -1 becomes 0, and -1 again becomes -1, and +1 becomes 0, okay? And 1. Okay? So at any time, this number, you can write it like this. Right? So because, you know, here your frequency of A is 4, right? And yes, you have 4 ones, okay? So this is X is, you know, frequency of A is 4, right? X is 1, right? And you also have 2 B's, right? 2 B's. So you have 2 of B, frequency of B, and -1. Okay? X, B is 1. You also have 1C, which is 1 and -1. Okay? So this is 4 minus 2 minus 1, right? So you can see this, they are actually equivalent. So we write this just for analysis purpose, right? When you actually run the algorithm, you just do a hash and a sum. It's very simple. Any questions about this? Because this Fs means so far the S appear Fs times in this room. So you add Fs so many Xs to this. Okay, if that is the case, then we can compute the expectation. Right? So keep in mind this XS is a hash, and it's a universal hash. Right? So it's a uniform distribution. Okay, so XS mapped to +1 and -1 with 50% probability. Okay? If you compute the expectation, it's like you know, 0.5 times 1 plus 0.5 times -1. Okay, the expectation is 0. Okay, expectation of XS is actually 0. Okay, keep this conclusion in mind. And if that's the case, now let's first look at it. If we just maintain the summation, is this enough? The answer is no, because if you think about some expectation of the sum, right? It's not a second moment. Okay, the expectation of the sum itself is not a second moment. Okay? It's actually 0. Okay, because using linearity expectation, you know, you can take expectation over this random variable, right? Because these are the constant, how many as you see in the stream. Okay, and we know this is 0. We just analyze this, right? So because of this reason, this is 0. Now your summation m times each item is 0 times some frequency. So the total is 0. Okay. So of course, if your expectation is 0, you cannot use this number to estimate the second moment. Right? Second moment is always a positive number. Okay, if it frequency is square. So okay. So apparently this is not okay. Right? But a minor revision of this sum, which is the sum square, basically, okay, is actually a good estimate, an unbiased estimate. Let's take a look at it. So what we do is we actually use a square of that sum, right? But we don't need to, you know, we just need to square it when we need, right? So when we maintain it, we just maintain the sum. Okay. So let's think about this summation, right? So this is the previous summation. Now let's square it, and then let's think about this exploitation, right? So what will be the result? So we will see some very interesting result here. And so firstly, you know, if you have a bunch of elements, summation is square, so you have A plus B plus C plus D squared. So it's equal to A squared, B squared, C squared, D squared. First, every element will be squared. That's because it's like you have another process this time. Okay, so maybe using ABCD will illustrate the idea a bit clear. You have A plus B plus C plus D again. Okay? Right. So now what you need to do is you know, the product is a bunch of terms. Right? 4 by 4 is 16 terms. Okay, the first term is A by A. Right? So you can also have B, and then you choose B also here. You have C, and you also choose C here. You choose D here. So this gives you this, right? Every element in the summation square. Okay, so this is the first term. The second term is then you choose A here, but you choose B here. So you can choose 2 different items here. Okay, you can also choose B here, choose A here. Although the result is the same. Right? So that's why you can write it like this. So you can have XSFS in the first process. Okay, then XT of T is a T's item in the second process. Okay, and then take this out. So this is what we can do here. And again, we require them are different because when they are same, right, it's already captured by this term. Okay. The reason we have 2 terms is because, you know, you can take S here, you can take T here. This is 1 term. You can also take T here, you take S here. Right? It's the same term. Okay. So basically, if we avoid redundancy, right, we only consider S and T pair of ones. Right? Then we have 2 such terms. It's okay. I hope this expansion will help you understand this. Yeah. I have a question. The question is the user who define which symbol maps to 1. Is there any special meaning for values 1 and -1? No, so the answer, the answer to this question is it's not the user. The user sample this frequency, sample a forward independent hash function whenever they do the computation. Okay, this is from ZP. Okay, once this function h is determined, okay, then this h function will automatically assign each item that you see to 1 or -1. Once h is determined, then it will, like apple will always go to -1, and the orange will always go to 1. Okay? But because we are sampling this h differently, each one is randomly sampled, uniformly sampled from VP. And maybe if you sample another h, then apple will go to 1 instead of -1. Do you answer a question, Jing? Yeah, it's a randomly assigned, you know, it's like a sample a function. So this is what we see earlier. Okay, so the randomness in randomized algorithm comes from the hash. The randomness comes from the hash function. Okay, look at here. It's a sampling a hash function from a hash family. Okay, the hash family is a uniformly, you know, A and B are randomly sampled from AP. Okay, so this randomness comes from the hash family. Okay, and when we talk about the FM sketch, we are saying that, hey, we want to make a uniform, right? We want to make a uniform. Yeah, this concept is very important. We want to make it uniform, so we will, let me see, where is it? We will first hash and then find the minimum value after hashing, if you remember. I cannot find where it is. And that randomness comes from hashing, right? But there's still some failure probability, okay? Like one third probability of fail. That's why we need to try multiple times, okay? And in our case, it's the same. The randomness comes from the hash family when you need to sample a hash function each time you do computation. And there will be some variance. The expectation should be unbiased, but there will be some variance. Then you try like a flip coin multiple times. Each time you sample, you will sample probably a different hash function, and then you cancel out the variance. You will see that shortly. All right, so yeah, here's what we have. Okay, so this is what we arrived here. And now let's think about right here. So remember, this is 4-wise independent hash function, right? XS is HS, by the way. Okay? This is 4-wise independent. Okay, 4-wise independent. If the two random variable x and t, right, are independent, then the product can be independent. We know that linearity expectation, but the actual product can also take expectation inside, only if these two elements are independent. Okay, so here it's 4-wise independent. Of course, it's 2-wise independent. It's more than 2-wise independent. So we can write the expectation into each. Actually, initially, because these are constant, right? You first write expectation of this, but then this can be written into this. Okay, and we know that this actually is a expectation is 0, right? Because it's a -1 and 1 equals 50%. Okay, both are 0. So this term basically is gone. Okay, this term is gone. This everything is 0. Okay, this is because how you sample the hash function edge. Okay. And then now, another interesting thing is this, right? So, this is 1. I hope you can see, right? Because it's either without square, it's either 1 or -1. But after squared, it's always 1. Okay, so this term is gone, and you get this because expectation of a constant is still the constant, right? And the questions so far? If this is fine, let's continue. Okay, so that's very interesting because what is this? This is second moment, right? Average frequency square and takes the sum. So we are saying, hey, even though the sum previously computed, this sum is the expectation is 0. Right? If you compute the sum square, okay, that expectation is actually the second moment. Okay, that's pretty interesting. Right? So we get an unbiased estimator, which is equal to this sum square. Okay, let's denote for simplicity of notation A as that unbiased estimator, which is the square of sum. Okay, A is a square of sum, not sum itself. Okay, that's it. Yeah, denote this. Right. So later we want to use Chebyshev to try to see, hey, how accurate we can treat. Right? And we can try many times to bring down the variance. Right. If you only sample one edge, this animation is gonna be variance is going to be big, right? Maybe each time you sample edge, even though the expected value is a second moment, but you may have a big bias from it, right? So you still need multiple tries, okay? It's like a flip a coin to bring the variance down, okay? And so let's denote A as this sum squared, okay? Now let's, so this, expectation, let's first consider, now it's more complicated, right? So A itself, keep in mind, okay, A itself is a summation square, right? Now what we are doing is, the estimator A is a square of sum. We are doing square of A, which is a square of a square sum, right? It's a cube, quadruple, right? So it's a 4 to the power 4, right? So it's 2 times 2, okay? Right. So that's why actually we require that we need to use a 4-wise independent hashing. Okay, so you will see how this is useful here. But it's exactly why we need a 4-wise independent hashing construct. So now let's think about what's the expectation of A squared. A squared, A is a sum of sum squared. Okay, A squared is sum to the power 4. Right? So this summation to the power 4. This summation is where we maintain in the string. Okay. Now we can write it like this, right? So you think about it, we have blah blah blah, blah 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 blah. Yeah. So each term, right? So it's a summation, right, from 1 to n. Right? Let's assume the first term we take a position s. Okay. The second term we take a position t. The third one we take a xu fu, right? The use position. SU. The fourth term would take a position V. Okay, it's V, UV in this place. Okay, then we'll get this. This is how we expand it. Right? And we're not saying that S must be smaller than T or U cannot equal to V. Right? It's really the general form. Okay, they can be equal. ST can be equal, and they can be either one is larger than another or another larger than this. Okay. Now let's take a look at this term. Right? So there are several possibilities. Right? Firstly, if you look at it, right? So it's possible that S and T are the same. Right? So another possibility, you can have, now you have 4 numbers, S, T, U, V. Okay, 4 positions in the sum. Okay? Therefore, there are several possibilities. One is this case, right? So all 4 numbers are the same, right? All from the second term, right? Or the third term. Right? So in that case, this becomes XS4. Right? Every T is also S, U is also S, V is also S. Right? They happen to be from the same position in the 4 parentheses. Okay, that will take product. So this is one possibility. Another possibility is 2 of them are the same, 2 of them are the same. Okay, so this becomes S squared T squared. So there are also 2 other cases. One is everything is different. Okay, so if everything is different, that term will be gone. Okay, because when you take expectation, you are taking expectation of this, taking something to this, taking to this, taking to this, right? Because this is forward independent, and you can write them out as a product of expectation of XS, expectation of T, expectation of U. Remember, XV is HV. H is the forward independent. After, if V is the forward independent, after taking H, it's still forward. Right? So then you can take product of potential. Right? Then it will become 0. Right? It's 4 0 times together. And there's another case that we haven't talked about. Right? So this is like all 4 are different. All 4 are the same. Right? Or 2 2. Right? 2 are the same. 2 are the same. There's also a case that one is V. Right? The other 2 are the same. Okay. Or equal to S. So it's like all 4 are different, or happen 2 of them are all 4 are different, and 3 are different, but 1 is the same as the other 3. Right? And you can say 2 of them are different, but the other is equal to 1 1. Okay, right? And then you have all. These are all 4 cases. You can easily verify. Now let's think about this case. Right? So we talk about the other case is this. 3 of them are the same. Okay, 1 of them is not the same. Right? If that happens, this thing is XS. I hope you can see that, right? Because this X, it can only take 2 values. If it's 1, after cubic, it's still 1. If it's -1, take cubic, it's still -1, right? So this thing becomes XS times TS, right? If you take expectation of that, you can again take it out. Right? So it's this is 0, this is 0. So these 2 cases all are different, or 3 of them are the same, another is different. These 2 will be gone, okay? Because the expectation will be 0. So the terms that are non-zero are only two possibilities. One is XS squared XT squared, okay? Another is XS to the power 4, right? So this is obvious, right? So once you have a square, so it's 1. Okay, all these are 1 because -1 and 1. Right? This is what you can take. After square, this becomes 1. This also becomes 1. Okay, cubic is itself, and quadratic, or to the power of any number that is even, then it becomes 1. Okay? Any number that is odd becomes XS itself. Right? Now, if this is the case, then we can eliminate most of the other terms. Right? So one thing is pretty sure, right? So if you have all of them taking the same position, you only have n terms. Right? Everyone takes the first position, everyone takes the second position, etc. But the other case is more interesting, right? So if you have 2 of them are the same, 2 of them are also the same, right? So then you have many choices, right? So for example, if you have parentheses, let's consider a case that like this. Right? So you want 2 of the parentheses take S, right? Another 2 take T. Right? there are many combinations there. So you can say, hey, the 2s are coming from here. Another can say, hey, these 2s come from here. Another can say, hey, these 2s should come from these, the first and the third combination, right? The other 2 are t. So how many combinations of this? Right, so this combination number is written like this. Okay, so let me see where's the one now. Is this now? Okay. So from 4 processes, we want to choose 2 of them. How many possible will true? Okay. So this also we can write it like C42. This number actually 6. Okay. So if you enumerate possibility like this, you will enumerate 6 of them. And 6 of them will all contribute to this term. Right. So we need to times this term with 6. Any questions? All right, so here we are specifying, hey, S should be less than T. T is starting from S possible. Then you are saying, hey, what's the smaller position? So how many of them are in different processes? Okay, then we have C42, right? So this is 6. All right, so then we change this number to 6, right? And we know these numbers are themselves 1, okay? And a 1 or minus 1 square is 1, okay? And then we can write it like this, and any 1 or minus 1 takes the power 4. You have this. So this may not be obvious to you, but we can think about it. Let's enlarge this term a little bit, okay? We write a 3 here, okay? Then you should be able to see this relationship, okay? Right, so, so this is, this term itself is what? This term itself is it's like a 1, every item itself square, because it's already square, it's to the power of 4, right? And then you have 2 ST, right? 2 AB, right? So you have 2, okay? So, but now you have 3 times that, right? So you from 2 to 6, and this from 1 to 3, okay? Right, so, but anyway, so this is upper bound, right? So if you take this out, of course it will have one share width, right? Because of course it will take one process from here, one process from here, right? All have the same position, you will get 1. But actually you have a constant 3, you have actually 3 shares. You make this even larger. But you will definitely have 2 AB, right? But now you have 3 shares become 6 AB. Okay, I hope you can see that. All right, if this is okay with you, then, what is this? What is this? This is sum square. This sum square, this is second moment square, okay? We know that second moment is our expectation of A. A is the estimate. So second moment square is our expectation of A square, right? I hope you can see that. Now let's use our conclusion. Right? So what is variance? Right? The variance is equal to your random variable square, take expectation, minus your expectation square. Right? So it's if you expound it by variance definition, we have seen that again. Right? It's like a -2 and a +1 of this. Okay, so you should memorize this thing. And if that's the case, then let's take a look. Right? So here we are saying that this thing we derive all the way, it's less than equal to the 3 times this, right? So this term is less than equal to 3 times. Then minus 1 term of this. So this thing is less than equal to 2 times expectation square, right? So I hope you can see here. So what are we doing here? What are we doing here? So why are we computing this? Why are we computing square of the estimate? This is because we want to compute the variance. Okay, variance A equal to the random variable squared. So why are we computing variance A? Because we also know the expectation A, which is it's this. Expectation A is a second moment. Okay. So this is because once we have the expectation, we also can compute the variance. we can use Chebyshev equality. Okay? So that's what we are doing now. So here we have an error bound that we can reach, which is the second moment. So of the second moment. So what we are doing is we want to, again, we want to, as we discussed, we want to sample many independent, so independently choose four wise independent sets of random variables. So we want to repeat this R times, okay? But each time we will have to estimate A1 to A. As I mentioned, each AI may not be accurate. Okay? We will repeat each time we choose a hash function from the hash function, but we will do this R times, okay? So if you remember, so we have the Chebyshev inequality, which says that how far away you are from the expected value. The probability that larger than C is equal to your variance divided by C squared. Now we are using C as epsilon E. Then this is epsilon squared E squared. Okay, this is using our Chebyshev inequality. Now the interesting thing is that you think about it, right? So this is the estimate of the sum, this is the estimate of the sum, right? So they are, each time their expectation is really your second moment, okay? But you cannot just sum them, right? So sum them, it's not enough. It's actually, we are using, we're computing A1 plus all the way plus AR, right? If we just take the sum, the expected value is R times our value, right? So we need to divide by R, okay? We need to divide by R. So this X here, it's like a law of large numbers. Is actually, then we do the previous one, right? Get the A, which is our estimator, for R times. And then we need to take the average of them. Right? Each one may have a big variance, but after we take the average, the variance will become small, okay? So here, for example, each of them have variance of A, okay? And they are independent. Each trial is independent. Independently sample from the hash family, hash from the big hash family, okay? Now we have R times, right? So what's the variance of X? What's the variance of X? The variance of X is a var divided by R, okay? How can you see that, right? So basically, if each time our variance is 100, if you try this, the previous sum, but each sum is using a different hash function, randomly sample from the hash family, right? You try 100 times, okay? Then the average value of these estimators, the variance will be reduced by 100 times. Originally, your variance is 100, now it will be 1, okay? In order to see that, you just think about that. So this conclusion should be memorized, okay? If you have the estimator and you repeat R times, the variance will be reduced by R times, okay? So just think about VAX, right? And you look at this R, right? Because, it's a 1 by R. If you take the constant out, it should be equal to V, it should be 1 by R squared, right? Because whenever you take a constant out, it should be 1 by R squared, okay? And then you have the variance of A1 plus AR. And because they are independently sampled from H, right? So we also have linearity of variance, right? So we basically plus all the way plus BR. Each of them actually have the same variance because they are from the same distribution. Right? So this becomes, this becomes R times your variance. Okay? And this R cancels with 1 square. That gives you complete. It's divided by 1 R. Okay? I hope you can see that. Any questions here? So this conclusion should be memorized. Okay? If each time you sample, and again, different trials should be independent. Okay? So when you sample this hash function H1, this H2, H2 is not dependent on H1. Each time you are randomly sampling. Okay? And then if you do different trials, the expectation is maybe 5, but each time you can deviate from 5 by a large margin. So this time 100, next time minus 100 or something. But if you try large enough, you can bring the variance down, okay? And significantly by I times how many times you try. So this is one conclusion here. The second conclusion is expectation, right? Expectation is the same, right? Because of linear expectation, this R times the EA and divided by R is EA itself. Okay, I hope you can see. Okay. And now we can just take the average of those estimators and what's the probability that they are different from the expected value by, let's say, an epsilon percentage, let's say 1%, epsilon can be 1%. Okay, if you are 1, now your expected value is 100, what's the probability that you are more than 101 or more than 99, okay, or less than 99? Okay, the probability is going to be bounded according to Chebyshev equality by this, right? And now we know that the denominator variance of X is basically variance of A divided by R, okay? And the numerator is epsilon squared times the variance of X. But variance of X is the same as variance of expected A, okay? Expected. So are we done here? Right, so variance A is that we have an expectation of A squared, right? We are not done here, right? So there's a variance, there's an expectation, okay? How can we cancel them? Right, so we have this conclusion. We'll say variance divided by expectation squared is less than 2, okay? So this is what we derived so far for the freeze. So then this thing is bound by 2, right? This R is divided, so this gamma can come down. So, and so we say, hey, this thing itself is divided, bounded by 2, okay? Gamma epsilon squared. I hope you can see. Right. Use our previous conclusion. Right. Okay, so now we know this conclusion now, right? So now the question is, what is gamma? Gamma is how many times you try, or 1 all the way to gamma, okay? Then we can set gamma equal to this value, right? If we set gamma equal to this value, so we are saying that if we set gamma equal to 2, right, by epsilon squared, there, right? And this 2 top and the bottom cancels. This divided by E squared at the bottom and this E squared at the bottom cancels, epsilon, no bottom, okay? Finally, we only have 1 by delta, but it's at the bottom, right? It's in the numerator. And 1 by delta, but this is 1 divided by 1 by delta. So this gives you delta, okay? That's how, actually this is computed in a reverse manner. You compute how many R you should, if you want to make the right-hand side there. But how interesting is this conclusion we have? So the conclusion tells you that if you use this hash family we used for wise independent we designed earlier, right? And you try enough times and you compute the average of your estimators, it's going to be pretty accurate, right? It's, if you want to, let's say, not too far away from expectation, let's say it should be within 1%, 0.01, okay? And so basically this epsilon is 0.1. So this is 10 to the power negative 4, 2, right? And square is 10 to the power negative 4, okay? Additionally is delta, right? So if you go beyond this, right? So we also want it to be less than 1%, okay? This is again, so this is 10 to the power negative 2, right? And this, if you compute gamma should R should be equal to 2 times 10 to the power 6. Right? Okay, so is it? So basically, we are saying this is called the epsilon delta bound. Right? So if you don't want to go error beyond epsilon percentage, and the probability that you violate will be, you go beyond this small error rate, the probability is going to be less than delta. Okay, this is epsilon delta bound. We say, hey, if you don't want to go beyond your expectation by 1%, right? You break this rule, guarantee only with 1% probability, right? Okay, less than 1%. And if you want this strict requirement, you only need to try 2 million times. Is 2 million estimator a crazy thing? Not at all, because you just maintain an array of 2 million numbers, which is not an issue here, right? You can create an array of 2 million items in your memory in gigabytes, okay? Right, so, and you can achieve very accurate result of second number, okay? So this is what we want to see. Another thing is that you can see, if you want to even more accurate, right, then you need pay more number of times to try, okay? And of course, the cost is linear to you, because when you compute the sum, right, you will maintain 2 million sums, right? each time you have a hash function, you want to compute too many hash functions. Each have sum to the respective sum. Maybe some are +1, some are -1. Okay. But again, this is quite affordable. Any questions so far? Because we are, this is the end of the class. Okay. And we have some reference for you. And again, so we have the company sketch, which follows similar idea of what we see so far. And don't be too worried, okay? They're actually, it's well defined. So if you cannot answer the question, you can read some documents. It should be figured out. Okay? And you have about 1 week to figure it out, right? So we will set the deadline. A little bit more than 1 week, I think. Okay. All right, so that's all for today. Any questions? Oh, there's a question on the expected length of the report final project, maybe 2 pages, but anyway, so the important thing is helping us to understand what you did, right? Evaluate your contribution. Okay. Right, so like we ask you to do data augmentation, rotation, etc., because it's a circular container, right? So if you rotate, you get a new sample, but it's kind of still valid. So, okay, and you can flip left, right, top, bottom. Okay, so these are still valid. And Keras itself, TensorFlow 2.0 itself has a data augmentation method. Okay, you can take a look at it. Or you can also use Behance share the link to do that. As long as it can be done, it's data pre-processing anyway. Right? So TensorFlow has a dataset class that can do. For an example of the report, we can upload a report for. I think if you go to my YouTube video for the last, final project of the machine learning class, you can take a look. They have some report and presentation there. By that time, we have more PhD students, so we can have more presentation. You can, if you think it's necessary, you can send me an email. I will send you a prior report, okay, as a sample. And we don't require you to be so detailed though, right? That's a PhD student's report. And we don't need to meet at the final exam time because this time we only have 1 PhD student, right? So we will upload the video. This PhD student will be joining, Kamo will be joining, okay? And I and the TA may be marking that, and we will share the video. But if you are interested, we can announce that time that we determine so that if you have time, you can join. It's okay? So again, in our YouTube channel, we have last time's final project presentation. We have 5 presentations. Okay, you can take a reference of that if you, at least for the PhD student, right? Come on. Okay, other students just report it from. But make sure your report can help us understand your contributions. Thank you. Again, I think no less than 2 pages, but if you want to write 8 pages or 10 pages, that's encouraged. Okay, no worry. Especially, I think you need to append some results, right? Sample images. I think definitely these 2 pages do not include the sample results. These additional sample results should be appended. Top 10, like the 10 sample results of your prediction. Yeah, I think so. So for Navi, I think you are present. Okay, I only marked 1 student present. I just double check. You should be present. You're welcome. Again, streaming algorithm sketching is very important stuff, but you don't have time to cover too many. So you will do the homework to get some feeling of that. So it's very useful. All right, so I don't see any other questions, and it's already 5 minutes past. So I will see you next week. Okay, next week will be the last class. We will just be a little bit relaxed and review some data sources that you can download your data and plot the tweets, right? And maybe also get like open data repository to help your data science project. All right, have a good night. Thank you. I will upload the 3 things, right? So one is homework 2, and another is behind prepare the documents and the final project documents. Okay. And thirdly will be the video. That's enough. Thank you and have a good evening.